Welcome to Lecture 9, Scheme Language, Functional Programming, Scheme Language. So today we would like to introduce a programming language for functional programming. The previous chapter 6, we are on functional programming and its application. And today we are going to introduce one language that is specifically designed for the functional programming. We pick the Lisp language. Scheme language. Today, our objective will be the scheme language, DrRocket programming environment, scheme, data type, list, function, conditional, and other programming structure, and functional programming using scheme. Overview. First, we would like to look at the Lisp language. Lisp language was created in 1959 by John McCarthy at MIT. It stands for LIST, list processing. So it was designed for list. So this language is a very old language. I think that it's as old as COBOL or any other language like Fortran. It was invented very early, and it was initially run on IBM 704, so it's a quite old machine as well. And it is the origin of the car and dar. Okay, car is the getting the first element, and CDR sometimes people call it card. Okay, so scheme language was developed in 1975. It is a dialect of Lisp. So Lisp, scheme, and Racket, these three languages actually is one same language. Except that scheme is a dialect, slightly different. It's named after planar and Conifer language. But the computer system then only allows 6 characters. Racket developed in 1975, so 50s, 70s, and 90s. We should say actually it's one language, but over the year it got improvements. But so far we have not seen scheme or Lisp or Racket to become really important commercial language, except that there is one other language. This other language is called EDIF, Electronic Design Exchange Format, Information Format. I'm sorry, I have a typo. So this is EDIF format. And this EDIF format, I'm sorry, this website may not be a good site. So let's look at this one called Wikipedia. So here we have the DAISY system, Mentor system, Motorola, National Semiconductor system. So you can see this EDIF format. It is very similar to the so-called Lisp language. Okay, so this is used because EDIF is prepared for markup. So many of the mask preparation for semiconductor are using the AND/OR function. So Lisp is a good choice. And EDIF can also be considered as a dialect of the Lisp language. So anyway, that's one possible application for this language family. So here we talk about the imperative programming language and the functional programming before, and today we are on the functional programming using scheme, Lisp, and Racket. Okay, so textbook, there are several sites, you can check them. Okay, you can check them. And tool, there are several tools as well. For us, we will be using this one called Racket language. So you can click this one. And this one is the site for Racket. We have this one called DrRocket, and you can click download. and you can install it. Okay, you can install it. Anyway, that is the site, and you will see something like this. So let's bring up the DrRocket. So I have installed it already. From left side, you should be able to download the DrRocket. So here I do have a copy of the DrRocket. So let me minimize the slice and put it on the left side. And let's wait for the DrRocket to come up. So Rocket is a new dialect of the scheme, but many features of the scheme language actually is similar to the so-called Rocket. So you can pretty much run the scheme program on DrRocket without any problem. So the system is coming up. Sorry for that. It actually may take a while for the first time to bring it up. It's coming up soon. While we are waiting, let's get started for this scheme language. So basic scheme language. Scheme is an imperative language with functional core. The functional core is based on lambda calculus. In this lecture, only the functional core and the simple I/O will be presented. In functional programming, parameter play the same role that assignments that do in imperative programming. Scheme is an applicative programming language. By applicative, we mean that scheme function is applied to its arguments. So basically, you have function, you apply to arguments, and it produces the return value. So basically, it is a function, and then you have arguments, and it produces the return. So it's a black box operation, okay? And it shares most of the syntax with this, but it provides lexical rather than dynamic scoping rule. And this scheme has found its main application in the field of artificial intelligence, rule-based system, and also the EDIF in semiconductor. The purely functional part of scheme has the schematic we expect of mathematical expression. One word of caution: scheme evaluates the argument of function prior to entering the body of the function, okay? And this causes no difficulty when the argument are numerical value. However, non-numerical argument must be preceded with a single quote that will prevent evaluation. So if you want to apply a function to a list, you better prepare it as a literal. Don't let this one got evaluated. And a quote mark will prevent the literal to be evaluated. Scheme is a weakly typed language with dynamic type checking and lexical scope rules. The structure of the scheme program, so basically you have function name and argument. That's it. That's the program, and you can expand it. Okay, you expand it. So right here we have plus 3 times 4, 5. This one you can consider it as the so-called prefix function. So basically it is 4 times 5 and then plus 3. Okay, it is this. Okay, and then we have syntax. Syntax: E is an expression, I is identifier, and K is constant. So an expression will be either constant identifier or this thing. And this thing actually is a expression 0 and expression star. So you have the recursive operation, okay, because the operation. So this one is a function, and you can apply this one to there, okay, and then you can have a lambda. So lambda is also expression and argument list and the result, okay, another expression. You can define a ID, okay, that can be available and some expression after returning the value. So these are the simple syntax of the scheme language, okay. So your expression can be a constant, okay, or can be an identifier, or it can be a function followed by expressions, okay. So this one actually is 0 or more, okay, 0 or more. So you can go this way, okay, and you may go back to here, okay. That is your expression, okay, and the lambda definition as well. At the start, we call it clean start, okay. So it means 0 or more time, So here syntax +3 means 3 + 5. Fact 6 means 6 factorial. So this one is 6 exclamation mark, okay. Append this one and this one. These are two literal, so they will be append together. I need to check the audio. Okay. Okay, so far these are the. I'm sorry for this. Let me check my internet. Okay, so there might be some problem with it. Let me close the possible YouTube site. Okay, let me clean things up. Okay, let me check my video one more time. Okay, bring this one up. Okay. Okay, let's continue. Sorry for that. So this one is a syntax of the so-called this scheme language. Okay. Okay, so there's a literal. Literal are numbers or list. Okay, and they are function called like this. So let's look at DrRocket. So DrRocket, when you try to use scheme or Rocket, you must put a language Rocket here. So here is an editor. Here is a environment, okay, evaluation environment. So here, when you first get in, you may have create new, okay, new definition. So right here, I have a new definition. So here I say, I can actually say define, okay, x equals 1, okay. So x equals 1, let me define it, okay. Okay, x equals 1. That's one definition, okay. Then here I would say plus x and 2, okay. So these two rule. So after having these two rule, I can use save definition as, okay. Save definition as. So I'm going to save into my demo location. So right here, I'm going to create a new demo folder that's called demo 9, okay, demo 9. So here I'm going to save it as here that's called program 1.rocket, okay. Program 1.rocket, you will create a file that is RKT extension file. So let's go there. Okay, under my this one, under my demo directory, I have demos 9. Okay, so right here I have a Rocket document, and Rocket documents extension will be, I check the property. So you'll be RKT file. Okay, it's RKT file. And scheme, sometimes I use a SCN. Okay, here I use RKT file. So with this two, I save it already. So now I'm okay to run. So click this green button, run. Okay, you got 3. Okay, you got 3. So right here, okay, right here, if I have the so-called square, okay, square, let's actually look at power, okay. So here you may have scheme, okay, and power, okay, power function. So power function. Scheme may have a power function, okay, exponent function, explanation, okay, simple explanation. So it's a power 3, okay. So it's a power 3. So here you have a power, okay. So power 3, 4, you will get 84, okay. So here you say power, okay, x2, then it's x squared, okay. So let's apply it. There's no such thing as power. Let me check, okay. Let me check. So here, let me check one more time. This one actually is power 3. This one, okay, you have to define the power function, okay. You have to define the power function. It's not free, okay. It's not given for free. So let me see, okay. Here, power function. You have to define it yourself, okay. Here, actually, let's see. There's no exponent function for free. Okay, sorry. There's no power function for free. So you need to define it by yourself. Okay. So this one may be later. Okay, this one may be later. So here you can use time. Okay, time x and x. Okay. This one we will get 3. Okay, and you can set the value. You can set the value. You can do SET. Okay, here in this you use a set Q, but in scheme you use a set exclamation mark. So set X, okay, using what? Using times X. So X squared will be used to set the value to X. Okay. So this one we got this. Okay, and then after that we can do this one. We can do actually time x1. Okay, time x1 actually you will get x itself. So basically you can evaluate x itself, okay? Evaluate x itself, and we can save all definition and run. Okay, x is not a procedure, okay? It's okay. X is not a procedure, so you can do this. Don't put it into the list format. And use outside evaluation. So that one is actually 1, okay. So here we define x as 1 and it's plus 2, okay, and the set q as e squared is still 1. So here let's do this one. Let's do set declaration x, okay, plus x2. So this one x will become 3, okay, becomes 3, and then we evaluate x. Okay, it becomes 3 over here. Okay. So that is the basic operations of the scheme language. Okay. The power function, we'll talk about it later. Okay, now, next one, data type. So the data type, you have the Boolean value. So Boolean value, you have true and false. So true will be punch sign P, okay. False value was punch sign F, okay. And other than that, these are 2 constants, and you can have many atomic variables, okay, or a string, okay, a string and value and ID, okay, and ID. Okay, A, B, C, okay, and these are all scheme, okay, we call it atom. Each one of the elements we call it atom. So atoms are used for variable name and the name of the function, we call it atom, okay. And this is an order set of elements consists of atom and other list. So A is an atom, B is an atom, C is an atom, 1A, 3 is an atom, A, B, C, D, E is an atom, 54, 18, they are atom. And with the parentheses, we call it a list. And this one is an atom, and this one is a list. Okay, this one is a list, but the whole thing is still a list. Okay, so that's list. List we can actually use a concatenation function to make concatenation of it. Okay, this one, disp and the scheme are different. Okay, so let's try this one out. Okay, try this one out. Concatenation is different. Okay, it's different. So let's actually save them. save the definition. So now let me create a new one. Okay, create a new one. And let me forget it. Okay, so this new one, let me actually save the definition as program 2. Okay, save as program 2. So this program 2, I try to create a list. So I say construct, okay, construct X, and then this one is empty list. Okay. So here that actually, okay, let me try this. Let me try on. Okay, don't try a list. So let me save it, and that's actually wrong. Okay, so it become a literal list 1. Okay, become a literal list 1. So here that's actually do define. Okay, define X equals 2. Okay, and that's construct. Okay, construct X, and here I just put a list, and it will be evaluated. You will be evaluated. Right here, this one, I don't evaluate that one. That's a literal list. Okay, so let's see the difference. So this one, we do that, and that is illegal application. So this one is not allowed. But if you do this, okay, if you do this, you actually you get a literal, they will be constructed. This will be constructed. Okay, that will be constructed. This is different from the Lisp language. Okay, Lisp language you do construct. Okay, here you don't have comma. It is okay, but here you do need to have a comma. Then that one will not be evaluated. Okay, so here if you want to construct 2 elements, okay, 2 elements, then what you should do is X and Y. So let's actually go back. So here let's define. Okay, let's actually do define Y equals 3. Okay, and then we do construct. Okay, so here I say X and parenthesis Y. Okay, second portion need to be a list. Okay, but this one will be evaluated. So if we do this one, okay, if we do this one, okay, right now if we do this one, okay, set definition, and we do construct. Okay, this one actually expect a procedure. Okay, expect a procedure. So that one is not okay. That one is not okay. You will evaluate that one. Okay, so here let's actually put this one there. So save definition, and let's go. Okay, so it become 2 and Y. Okay, become 2 and Y. So here, if I don't want my X to be evaluated, I don't want my X to be evaluated, I will actually do this. Okay, don't evaluate my X. Okay, it will become XY. Okay, it will be a literal of XY. So if you do not use the quote mark, then the value will be evaluated. Okay, will be evaluated. So that's the rule. Okay, that would be the rule. Okay. Anyway, this one is making a list. But how about if I actually do this? If I construct and using X and Y, what will happen? Okay, here you use X and Y. You create 2 and 3. Both are evaluated, and it doesn't create a list. This one create a pair. Okay, this one create a pair, and there's a dot in the middle. This one create a list. Okay, and semicolon is used for comments. Okay, it's used for comments. So those are comments. Okay, so let's run it. Okay, so let's get the result. Okay, we get the result. Okay, so that's that. So there's a pair, there's a list. Okay, we'll talk about pair later. Okay, we'll talk about pair later, but must remember the way we construct a list. Okay, so these are a list of elements. Okay, and an atom is a single element. And we will have numbers, integers, real, rationals. Okay, you can put integer, real numbers, rationals. Okay, these are different way to put them. Okay, and symbols. Okay, symbols. You can put symbols in there, and this different thing. Okay, and you can have a string. Okay, so let's try to do this one. Okay, so right here, That's actually define, okay, str, okay, equals a, b, c, d, okay, and then b here, and let's actually do this one, okay, define str2, okay, x, y, z, okay, and that's wrong, okay, this, okay, and let's actually put over here, okay, append, okay, str, and str2, okay. So this one is used for a pen, okay? They are used for a pen. You cannot use a pen, so let's use a plus sign. It is still not okay. Okay, so here let's go to scheme, okay, string concatenation. So string concatenation, appending, okay, there's a user menu here, okay. So let's see this one. We need to be scheme, okay, without space. Concatenation is scheme without space, okay. So this is used for, okay, there's a function called string append, okay. There's a function called string append, so it's called string append. That's called string append, okay. Now we'll append the two lists together. Okay, so now let's actually define another one. So let's define, okay, light speed C as 3E8, okay, light speed C, okay, and then actually times C2, okay, whatever. So let's go on this one. Okay, so that is the function. So the scientific notation still work over here, okay? So real number use scientific notation here. So that's the rational, okay, rational. So we can define, okay, define, actually, 2/3, okay, let's define 2/3. So 2/3 would be 2 divided by 3, okay, and that's actually times, okay, 2/3 is 2, okay, so that's wrong. Okay, it becomes this. This is the so-called rational number. So rational number is a data type in scheme language. Okay, rational number. So you have integer, you have real number, you have rational number as numbers in scheme language. Okay, and you also have the Boolean value. So you can have here. You can have define. Okay, define Boolean value number 1. Okay, greater than, okay, 1 greater than 3. Okay, so this same, and then that would be B1. Okay, B1. So B1, okay, and here you can have a end function. So end, okay, let's see, end B1 and 2. Okay, B1 and 2. Okay, B1 is false. B1 and 2 will be false. Okay, that's the value we get. Okay, so that's the Boolean value. So here we demonstrate the string, Boolean value, and also integer, real number, and rational. Okay, character you can use a C. Okay, so let's look at characters. Character C. Okay, character C. So let's define. Okay. Actually A, okay, a sharp character A, okay, so something that is justified, okay, B, okay, character / B, okay, and that's actually do string and okay, A and B. Okay, that's not allowed, okay, this one not allowed, okay, so character. So we have a character. So how about this? Let's actually do, don't use a string append. Let's actually do greater than, okay, greater than. And it cannot be used for greater than comparison as well, okay. So here, this one, it is different from the Java we know, okay. different from that. So let's do scheme, okay, characters. So scheme has characters, okay, scheme has characters. So character is like this one, you have the different letters, okay, different letters, okay, and there are some other letters, okay. There are some special letters. So you have character, okay, this one character, this one name, okay, and that will create a name, okay. So this one character name T, okay, char T, okay. So that one will be string append, okay. So that's tradition. This is character name, okay, character name. So here, this one you have this one, and that's actually to this one. Character, okay, name, okay, A, okay. That actually is a character name. Okay, let's look at it. This one is called character dash name, okay. So we character dash name my A, okay. And then here, let me also do this one, character dash name. So that actually getting the string, and these two become two string, and I use string append. There's no such thing as character name. Okay, let me see. So this one, it is character name. Okay, use it. Let's see. Okay, this one's wrong. Name to character. Okay, name to character. So character to name. So there is a procedure called character to name and character. Okay. So character to name. Name is that. So let's actually try this one. Okay. So let's try different way. Okay. So here, let's do this one. Character to name. How about character name is for my A. Okay. So this one not okay. So let me try different one. Let me try sharp / A. Okay. So that's not okay. It doesn't take this one. Okay. This one is MIT. Okay, MIT procedure. Okay, let me see. So let me try different one. Okay. Character and string in scheme. So we do have sharp, this one that's actually a character, okay. And you have character to integer, okay, integer to character, okay. Okay, so let's try this character to integer. Let's try this one. So we got a character and we try to convert it to integer, okay. So let's try this one. Okay, so it's okay, we'll convert that to integer, okay. So that is a character. So this thing is a character. Okay, so here let me actually convert this one to the so-called name. Let's see. So it doesn't take the character to name, okay. So let me keep this one character to integer, okay. And let me also try this one, integer to character, okay. This one applying to my 98, okay. 98 should give me the B character. Okay, that's a B character. So now that's actually we need to convert character lowercase. So these are different functions. Okay, these are different you can convert to checking for it is a lowercase or not. Okay, and here that's actually C. Okay, string. Oh, okay, you can make string. Okay, you can make string. So that's make string. Okay, that's make string. So we can do make string one copy of my sharp expression A. Okay, so let's try this one. Okay, that's A string. So this one, let's do make string 10 of my A characters. Okay, so you get A. So to convert it to string, use maxstring function. Okay, maxstring function. So this one is a collection of the so-called character and string functions. Okay, this one you can search for it. Okay. Okay, so here we briefly go through the character and string in this portion. Okay, and so the different data type. And let's continue, okay? Let's continue. So here we finish that, and primary data type, okay, case is generally not significant, okay? And we have plus, minus, okay, exclamation mark, different operators, okay? An operator, you have plus, minus, actually divide, okay, multiply, absolute value, square root, okay? You have this different operator, basic math operator, relational operator, equal checking, okay, UQ checking, logical, okay, double equal sign checking as well, okay. So, okay, equal sign issue is equal checking, okay. And you have the short circuit logic operators, okay. And predicate, okay, predicate is number, checking for number, checking for string, checking for Boolean, checking for pair, checking for symbol, okay. These one are predicates, okay. Applying operator, okay, to function. So you will apply the function among these different arguments. Okay, that's a function call. Okay, this one is a function call. So here we do have plug 2, 3 that will get the result of 5. Absolute value of -4, you get 4. Time 2, 3, that would be 6 plus 6, 8, you get 14. Plus 3, 4, 5, 1, that will sum them up together. It will be the same as your reduce function, okay, reduce function in Python, okay. So pair and list, if you construct the two numbers, you become a pair, okay. If you construct two strings, that would be a pair of strings, okay. This is different from this. It's not this. It's actually called pairs, okay. So pairs. Okay, pairs is like a map, okay, like dictionary or map. Okay, so you can construct this one and you card it, you get the first element. You card, you get 2, okay, you get the second one, okay. And you actually do pair empty, okay, empty, you get false, okay. And then you construct 1, 2, that's a pair, checking is pair, is a pair. If you do list 1, 2, 3, that would be a list, that will not be a pair, okay. Okay, so here we have defined a list, that's listing 1, 2, 3, 4, 5. This is another way you can create a list, okay. And then you call the list, you get what? This one, you have a list. So a list is a list of 1, 2, 3, 4, 5, okay. And you will make a list. So a list is this one. You call it, you get 1. You CDR it, card it, you get 2, 3, 4, 5. Checking if it is a list, it will be 2. Checking if it's a pair, okay. If it's a pair, you will also get 2, okay. And define a pair, construct this to a pair, and you will get a pair like this. Call it, you get 1. CDR it, you get a second one, okay. You get a second one. Is it a list? No. It is a pair? Yes. So remember that if you check a list for pair, it will be true. You check a pair for list, it is false, okay. It is false. So here we have a listing of this function, length equal, okay. Equal will test the two lists are equal recursively, okay. EQ will test the reference value of the two lists, only the edges, okay. Card will be the first element. CDR card will be the rest of the list. Construct will make a new list cell, okay. And it construct actually is should be element and list, and you will do construction. But remember that these two, you may like to use a quote, so make them no evaluation. Otherwise, you will be evaluating it, and then construct. Okay, but you may want to waive the evaluation. Okay, and this will make a list. Okay. So these are different list functions for the list. Okay. Variables. So scheme have both logical and global variables. In scheme, a variable is a name which is bound to some data object. Okay, so we do define a symbol with some expression. Then the symbol will be actually be associated with the result of that expression. Okay, this actually is a binding. Okay, so define is a binding. Because this language is supposed to be pure functional programming. So define, set exclamation mark. These are actually creating variable, creating state. These are not pure functional programming features. So we can define x equals 1, set q plus x1. So here actually x is 1, it will become 4, so x become 4. Construct x with an empty list, then it will become a list of 4. Variable, the line below declare a variable called clam. Okay, and we do have a clam. Okay, set its value to 17. And we can define a clam with 23 and plus clam 1 become 24. Define bird equal this ABC list. Okay, define early to burst. So early and burst right now become two same reference that pointing to early. Okay, that actually make this one. Okay. So actually scheme use a pointer. So both bird and early both pointing to the same list. Okay. So we will only use define to bind global variable, and we won't rebind them once they are bound. Okay. So you cannot redefine the same function. So here we can have the LAT. LAT will actually create local binding. Okay. So it's a lexical binding of the second of some scope variable. So that function, it will be binding, and a list of binding, and that happen, and that will apply to all the expressions. Okay, that is the so-called application. Okay, so you have a binding, and different applications. Okay, so this is the general form of that. Okay. So here define R2x, okay, append reverse x. So x will be reversed, and x will be reversed, and append these two reverse, you append them together and return the result. Okay, that's a double reverse. So this one you can let R to be the reversal of the x. Okay, so here you create a list of binding, and that will be applied to this append function, and the result of this one will be the you define. Okay, so let's actually look at this one. So here let me actually save definition. Now I will create a new one. So this one called double reverse. Let's actually do define. Okay, define. Okay, here we will have the so-called R2, okay. R2 is a function name, okay. R2 is a function name. So R2 will take parameter x, okay. And you got an x, and you will use what? That will create a list of binding, okay. So the first binding is called R, okay, reverse. Reverse will be the reverse of x will be bind to R. Okay, and this is the only binding we have. So here we have this binding. Okay, we have this binding, and this binding will be applied to the result we have here. Okay, so we will do double reverse. Double reverse, we will do append your R and R, okay, together. And this whole thing is the domain of the dot, and we put them into define, okay? So here after this, we are going to apply R2 for the list of the 1, 2, 3, okay, and that will be my list, okay, and I'm going to apply my R2 to this list, okay. So this one I'm going to call it program 3, okay, program 3, and I'm going to run it. There's unbound reverse, reverse. I'm sorry, I have a typo. Reverse. I have a typo. Sorry for that. Okay, so it reverse and then double binding. Okay. Okay, so that one is our reverse function, and we do double reverse. Okay, so that that will create a scope. Okay, so that's that. Here, following that will be a list of binding. Okay, and then that will actually apply the list of binding to the evaluation later. Okay, and we also have a lat star. And the problem with a lat is that while the binding are being created, expression cannot refer to binding that have been made previously. Okay, for example, this does not work. Okay, so if we have lat x3 y plus x1, so this lat, okay, that x3, this one is older one. This one will not be using the previous lat. Okay, will not be using the previous lat. Okay, and the y will not get y. So this one we will use lat star to actually let the previous binding to be available. Okay, so let's try this one as well. So this portion, okay, so let's actually do this. Okay, so here let's do this one. Let's do a lat. Okay, so let's use a lat. Okay, so here lat, I'm going to use lat. Actually, we'll define x to be 3. Okay, we define x to be 3. So we actually bind the so-called x and 3 binding together. Okay, so 3 binding with x together. And then we have y. Y will be binding with plus y, okay, plus x and 1. So y binding to this, and this is a list of binding. And this list of binding will be append to what? Plus x and y. And we do this one, and that's finish the lat. And we save, and we run it. Okay, x is unbounded because this one binding will not be applied to there. So right here, let's put a star in there and save and run, and it is okay. We get 3 plus 4, we get 7. Okay, so that's the that and that star. Okay, the difference between these two functions. Section 5, function. We are going to talk about function, including the define of function, the use of function, and also the anonymous function. First, let's look at the definition of a function. The definition of a function first, you need to use a define. So define, then you bind in a function name. So here, that's, for example, you have the function name maximum. Okay, so let's try to use the word big. Okay, and you have 2 variables x and y. Okay, 2 variables x and y, and then that's your function name and parameter list. Then next one, you will return the value. Okay, so here you would have the function name and parameter, and then you need to put your expression for the value right here. So the expression of the value, this time I will use condition. So condition will set up several conditions. So say 2 conditions we actually will use. One is x greater equal to y. So when x greater equal to y, if this happens, okay? And in this case, this condition, we are going to return X, okay? We are going to return X. Okay, second condition. So this one is condition. This one is for define. This parenthesis is for condition. And then this other condition will be else condition. So L condition, okay, this L condition, second condition. Here we have this one, L condition, okay, L condition. Okay, so here we have too many, okay. So L condition will return Y, okay. So this one, actually, let's save this function. So this one, let's call it program 4. Okay, and with that, that's actually run big 5 and 2 and run big 2 and 5. Okay, let's save and that's wrong. Okay, both of them will get 5 as the maximum value. Okay, so basically this is a function. Let's try another function. So here let's assume we have define a function, and this function is the sum. We have the x and y, so 2 parameters, and we will return the value here. Okay, we'll return the value uses plus x and y. That's the return value. Okay, so here you have a define and function name and the parameter list in the list, and then the expression in another list. Okay, and we will sum, okay, 2 and 4. Okay, let's actually save it and run. So these are the definition of the functions. Okay, that's normal function. That's normal function. And next one, let's actually look at this lambda expression. So lambda expression is an expression that will evaluate and provide you some value. Okay, that's lambda expression. But lambda expression by itself, it has lambda and parameter list, and the value will be provided. So this one actually is a expression, so return some value, but it's not a function, so you cannot use it for calling. Okay, so here let's actually define a function. This function called sum with x and with some value. Okay, so that's actually have x and y. Okay, 2 value. Okay, these 2 value. And then we will define a lambda expression for this one. So let's actually have the lambda expression. So lambda expression. This lambda expression will take the value of x and y, and we are going to evaluate plus x and y that actually is for lambda expression. Okay, and this one is actually called sum1. Okay, so here we can run sum1, 3 and 4, and let's save it. And that's wrong. This one is a procedure, okay? It is a procedure. So lambda expression sum1, we have x, y, we will do sum. So that's lambda expression. Okay, let's try this. Okay, this is lambda expression. It will use the parameter of a and b, okay? And here we have this one plus a and b, okay, and this whole thing is a lambda expression. Okay, that is a lambda expression, and this lambda expression we will apply to the lambda expression is a function we apply to x and y. So let's save. Okay, that will get 7. Okay, that will get 7. So lambda expression is a function we put on the expression part, okay, and the parameter will pass over, and we do this. Okay, this will run the lambda expression. So lambda expression is an instantaneous function, or you can call it anonymous function that you can apply to some location. Okay, apply to some parameter list. Okay, parameter list. So something like that. Okay, so something like that. Okay, that's lambda expression. Lambda expression, we can have lambda expression s1 plus S1 and S2, okay, and you perform this one, square of this, okay, this is lambda expression. So this one will calculate x1 minus x2, okay, square, okay, that actually is lambda expression, okay, this is a lambda expression. Okay, so we can actually say square difference, okay, square difference. That's that. Okay, so let's actually try this one. Try this one, square difference. So this one we can define another function, okay. Define another function. So let's assume that we actually have the function that we actually calculate the distance. Distance would have 0.1 and 0.2, okay, 0.1 and 0.2. So this 0.1 and 0.2 will calculate the distance. And this distance will have the, actually will have a lambda expression, okay. So lambda expression. So this lambda expression, we actually bind in the S1, Y1, and S2, Y2, okay. And we are going to calculate the result using the square root of the following scene. So here is a square root was square root of the plus sign, okay, plus sign of two scenes. Two scenes, it is times, okay, of two scenes, okay, and here we have time of two scenes, okay. So this time will be S1 minus S2, okay, and here will be S1, okay, minus S2. So this one is the square, okay, square of S1 minus S2, and this you have Y1 minus Y2, okay, and you have Y1 minus Y2, okay. Okay, so here we have a square root. So square root, you will use the P1, P2, apply the lambda expression. So lambda expression, okay, lambda expression is up to here. Okay, lambda expression up to here. So this lambda expression will apply to, okay, this lambda expression, we have this lambda expression, and this lambda expression will be applied to, okay, it will be applied to some value, okay, based on the P1, P2, it will be applied to some value, okay, and this some value will be defined here, okay, and the finish of the define will be here, okay. So here we will have some value based on P1 and P2. P1 and P2, we have to find the X and Y, okay. So we would do car of the P1, okay, car of P1, okay. And this one will be S1, okay, S1, okay. So here we are going to apply this thing to this one is actually the parameter list, okay. So you put the lambda expression up to here, okay, up to here. So here your lambda expression up to here, and you put your parameters. So first one will be car of the P1. And then you have car of the, you have the Y1. Y1 is actually card of the P1, okay? And then you have car of the P2, and then you would do card of the P2, okay? And this one is to finish the lambda expression. Okay, now we actually finish the define of the distance. Now we will actually do the following. We will actually do here define, okay, define P, okay, P will be using construct of the 1 and 2, okay, that is the P, okay. Then another point we say define Q, Q is another point. So we use a construct, okay, 3 and 4. So 1, 2, 3, 4, they are 2 points, and we do distance of P and Q, calculate the distance between P and Q. So here, okay, here P is a pair of 1 and 2. Okay, this one we have another one. Q is another pair of 3 and 4. Okay. And this one will calculate the distance between P and Q. Okay. So let's save. And we'll calculate distance. Okay, let's see. Here we have identifier x1 minus x2. The lambda expression, unbound parameter. We do have x1, x2, x1 minus x2. Over here you have the parameter list. Okay, here you have a parameter list. So you need to buy this one. Let me check. Okay, this one is this your lambda expression. The lambda expression up to here. Okay, so you have P1 and P2. P1 and P2. You apply to the value here. You have the car or the P1. Okay, and car or the P2. Okay, right here. Okay, let's see. You have car or the P1. You have car or the P2. Okay, let's see. Let's save. So here we have the A, S1, S2, Y1, Y2. Okay. Let's see here. You have time. Okay, I'm sorry. This one is wrong. You need to use minus. Okay. I have the syntax error. Okay. Sorry for that. I'm using the wrong syntax for it. Okay. Sorry. Okay, let's actually save one more time. Long it, okay, and here actually a argument. So you actually, okay, these two we do have plus, okay. So this one, let me see. Okay, one more. Okay, here we have minus. I put a minus at the wrong location. Okay, sorry for that. One more time. Let's see. Okay, that's actually wrong. Okay, so this one you get the value. Okay, so well you can see that actually the DrRocket can help you to do debug. Okay, it do show some error message, but you need to be able to read the error message. Okay, DrRocket is a good tool. It has good error reporting system. Okay. You help you to do the debugging. So that's, well, we can use the lambda expression to define a function as well, okay? But sometimes you may or may not need it, okay? May or may not need it. Okay, so like that, okay? So you have function, define function, and then you put a function name and the parameter list, okay? So let's see here. Okay, that's lambda expression, and you can define a function and function name and parameter and the expression to return the value. Okay, so we can define double x and then return x time 2 times x. Okay, and we can define this one called centigrade to Fahrenheit. Okay, centigrade to Fahrenheit. We calculate the temperature conversion. Okay, define x10, so x equal 10, and you add x and plus x1. Okay, so x is a parameter. You increase the x, okay, by 1 and return the value. Double 8x, you will add 1. Okay, add 1, call this one. You put 8x by 1 and double it. Okay, double and add 1. Okay, so double 8x, x is 10. Okay, and add 1 is 11. Double will be 22. Okay. So we can define test 3. This one test with no parameter, and you run test, you will return 3, no matter what parameter it is. Okay, and define not a function. Now a function 3. Now a function is actually available. Okay, So you do this, you revert 3. But if you evaluate not a function as function, you don't get it. Okay. So here these are the sample code. You can find it in example 3. Okay, in our lecture sample code. Okay, equality. Okay, equality checking. You can use UQ question. You can use double equal sign. You can use UQV. Okay, you can use equal. There are several different ways to do equality check. Okay, let's do it one by one. EQ is pointer comparison. Okay, return true if the argument literally has the same object. Okay, so EQ is pointer comparison. Okay. UQV, okay, actually that the right thing when comparing the numbers. EQV is equivalent evaluating the values. Okay, so EQV is for that. Okay, equals return true if the argument has same structure. Okay, formally we can define equal. Okay, recursively. Okay, so basically it need to be have the same structure, say a list or list of list. Okay, you return true if actually the whole program we go and evaluate it recursively. Okay, that's called equal. So equal is recursive evaluation. Equal V actually is for the value. Equal is for the pointer comparison. Okay, so right here we have claim 1, 2, 3 is a list, and aptus claim. So aptus and claim both are pointing to a same list of 1, 2, 3. Okay, and aptus. Okay. So now equals evaluating these two is the same. Equal of claim and claim is the same pointer. Equal claim and aptus is the same. Equal claim and 1, 2, 3, they are different pointer, different location. Same value but different location is different. Equal for these two, they are also different location. Equal 10, 10. 10, 10 is the same same value. Okay, 10, 10.0, 10.0 is false. Okay, this one is value is the same, but actually it's not the same object sometimes. Okay, so equal values 10, 10, that's actually true. Equal 10.0, 10.0, that's actually true. Same value. Okay, equal 10.0 and 10 actually it is different data types of false. Equals claim 1, 2, 3 equals a recursive structure to evaluate. So it's the same. These two also the same. Okay. So that's a definition of equal, equal V, and equals. Okay, that actually is the definition. So double equal sign is comparison two numbers only. Okay, two numbers only. Logic operator. So you also have a logic operator. Okay, for comparing two numbers or some other things. So you have AND that actually is combining the logical expression. Okay. Or that's OR operation. So everybody know it. Okay. Not is the negation. Okay. Not is a negation. So here this one not equal 10, 20. You can also rewrite it as not equals 10 and 20. Okay. That will give you the same result. That's a logic operator. Okay. Conditionals. So you have a if condition, true expression, otherwise false expression, and this one will return one of the expressions. So this one is conditional statement. So here you have if equal 5 plus 2, 3, 5, and the true portion you return this one, else you return this one. Okay. So this is that. Okay. So here you can use these greater equals 10. So this one is different from condition. Condition, you have multiple expression. This one, you only have if, then else. Okay, two part. Okay, two part. So conditional statement, you can test several conditions. And the last one, default condition, you use else. Okay, you use else. This one a little bit more like switch. This one more like normal if, then else. Okay. So here you have F, okay, F greater than 60, you say too hard. Greater than 60, but less than 80, less than equal to 80, we say nice. Less than 35, we say too cold. Otherwise, we say, okay, typical temperature, okay. Section 9, skin cheat sheet. in this section, we are going to look at a few examples of the programs. Scheme is an extraordinarily simple language. It implements just a few fundamental concepts that can be combined in interesting and powerful way to build a complex system. So here we will give you the example of a few programs. This is the heart of scheme interpreter. The evaluator implement the following algorithm: evaluate. Is expression an atom? If it is self-evaluation, just return it. Otherwise, return its value from the current environment. The so-called current environment is the current reference environment. Else, if the expression is unleashed, then we use the first element as the spatial function, and then use that function to work on the other elements. Otherwise, evaluate the first element of the list and apply it to the value of the rest of the list. This is evaluation. And then here we have defined x10. So define assign a x with 10. Then we have defined double, and double is a lambda. Double is a lambda. So here define lambda. This can also be considered to be a function definition. So we can quote hello, quote hello, you will get hello. Okay, you can quote. So quote actually means no evaluation. So 1, 2, 3, you quote. Okay, that's actually the quote mark. Okay, so this quote mark is also the no evaluation mark. So lambda x plus x10. Okay, this is a lambda expression, and define plus 10 and using this lambda expression. So this one you have a reference, while this one you don't have reference. It's anonymous function. Okay, condition is a general condition. So you have a condition and then you have a condition list. Okay, so first condition and first return expression, second condition, second expression. Okay, something like that. Okay, let's continue. So that and that start. This one is binding. So here you have a binding list. You bind x equals 10, y equals 20, and then you use that to apply to this. Okay, so that's the lat operation. Lat and then binding list and then expression. Okay, so this show you the result of these different functions. Okay, built-in types and functions. Schemes support numbers. Okay, integer, rational, floating point, characters, string, boolean, symbol, list, and vector. Below are some examples of these built-in functions. So let's look at it. We have plus, but actually we'll get a sum. Where equals will be the equality check for numbers. So equals, greater than, less than, equal, and less than. Okay, here we have the equal. This equal will be checking the reference. So you got false. So quote hello, quote hello. This one the same reference. Quote this. This one actually checking the reference is different object. So it equal. Quote will check the recursively. Okay, so this one is the same. So define full as this one. So it's a literal. Bar pointing to the same reference. So equal checking the reference, they are the same. Checking the content, they are the same. Okay. So these are the functions, built-in functions. Okay, here we define full as this. Okay, and then we have defined bar. Bar is making 3 a list and construct 2 to the list, and then construct 1 to the list. So you create 1, 2, 3 list. Okay, and bars actually making list of 1, 2, 3 and assign to it. So basically, these 3 actually will get the same result. You will assign the 1, 2, 3 to who. This one also will assign 1, 2, 3 list to bar. This one assign 1, 2, 3 list to bus. Okay. But remember this one, the last one, making this one not Rocket. Okay, not Rocket. It is a scheme format. So next one, null. Okay, check it if it's null. Okay, check it if it's null. Card, you will get the first element. Okay. Card, you will get the list, the rest of the list. Okay. Card and cut. Okay, this one like that. Okay, so iteration via recursion. So here we want to work on the getting the power of x raised to the power n. Okay, so that's the lambda, that's exponent. So when n equals 0, you return 1. Okay, then every time you do recursive calling x and then n minus 1. Okay, and then times 1x. So keep doing that until you hit the return here. Okay. And checking the list similarly, you actually check if it's a null list. Otherwise, you actually check the length of the rest of the list and then plus 1. Okay, that's actually using recursion to replace iteration. Okay, higher order functions, you have compose. Compose, you have fg and then x, you can compose. So this one is compose, means you have function 1, function 2, and then you will create a new function that's called this one compose function. So compose function will create a function that will take this. Okay. Okay, so compose, you get the even as one function, even checker, and the lambda function. So lambda function is internal function. You will get what you get here. You have get x. Okay, and this lambda function is x decreased by 1. So you apply this function to 10 first, then you become 9. 9 is that even? No, it's not. So you get false. Okay, this one you have the map function. Map function, you have the list and the function. So you are going to apply this function to all of these. Okay, so what you will do is actually when this null list, you will return the A list. Okay, you will return the A list. Okay, that is a null. You will return the null list. So now you construct your car and then apply the f function to it, and then continue to map your f function to the rest of the list. Okay, and you construct this one element to the list you get. Okay, so basically you got the last one as empty list, and then the one before the last one you apply, you have an element, and that is one f or x operation, and you continue to do that. Okay, for the rest of the list. Okay, so that is the map function. Okay, so map function. That is, so we right here apply the even function to every single one of them. Okay, to every single one of them. So we got false, true, false, true, or 1, 2, 3, 4. Okay. Functional programming in Scheme, section 10. Okay, right here, lambda calculus. A calculus is a method of analysis using special symbolic notation. So basically, left-hand side is a function, right-hand side is a lambda expression. Lambda expression, lambda parameter list, and then the expression. Okay, and you apply lambda expression to 3. Okay, so left-hand side is a function, right-hand side is lambda expression. Okay, so that lambda calculus. Okay, lambda calculus, you have f of xy equals x minus y. So you have lambda x, lambda y, and then returning the expression x minus y. So you have this, okay, and your parameter this is this, and this is one more expression. So that actually is another expression for lambda calculus. Okay. So okay, so here let's see. Let's continue. Okay, function map a one element to from a domain to the range. That's called a function. Okay, domain can be, you have to know about your domain and range. Okay, but remember that in functional programming, you can put another function or a data. Okay, and then you can create a function, or you can create some value. Okay. So that's the functional programming, and no side effect. Okay, we assume no side effect and can be composed. So this data structure is the workforce. We use this data structure mainly. Okay, program data equivalence. Okay, heavy use of recursion, usually interpreted, but good compilers exist. Okay, so that's the for scheme language. Okay, here we have eval function. So eval function is very useful in this. Okay, so eval something. So y is making list of this plus x and y a list. So you create list of plus x and y. okay, and that is a expression. So define S3. So X is a function. It would actually okay. This define S3, so S would be equal 3. Then S is put in here is actually is a plus 3 function. Okay, and Y is the this one plus 3, 5. Okay, and then evaluate Y is such a list, and you get the environment. Okay, user initial environment. Okay, you get that. So here, this one you kind of need to be careful. So let's look at this example. This one is not what we actually usually see. Okay, so this one, let's actually look at here. So let's do this. Let's have let's actually save this one, this program as okay. Here, let me save it as program file. Okay, let's save it as program file. Okay, so program file, I'm going to do define X and 3. Okay, X and 3. So here, if I evaluate 3, okay, I evaluate 3, I save and I run. I get 3. But here, if I do, okay, here I do eval 3, eval X. Okay, I save this one and I try to evaluate X, and it actually not allowed. It is not allowed, so I do eval X and then I say user initial environment. Okay, so user dash initial environment, something like this, and we save. Okay, so this one, wait, there is no such thing as initial environment. Did I spell something wrong? So user initial dash environment. User initial dash environment. Okay. So this one may have error. Let's actually check it. Okay. Let's check it. Okay. So here, that's actually in user initial environment. I may have spelling problem. Okay. Here, let's see. Let me see. Okay, let me see. It's not allowed, then we need to find the, okay. So here, let's see this one. This one actually initial environment, it actually is not allowed. Okay. So let's do the other way. Okay, let's do the other way. So right here, let me actually create a namespace. Okay, let's actually continue our slices and then look at it. Okay, so this one apparently doesn't work so far. Okay, doesn't work so far. So let's continue. So here is evaluate the initial environment that doesn't work. Okay, so let's actually look at it. Okay, let's continue how to look at how to define the binding reference environment. Okay. Okay, so here you directly eval this one. Okay, it's not allowed in the defined area. Okay, so this one evaluate this one. Okay, but you put it over here, it would be okay. So let's look at here. Okay, so let's try this one. Okay, so here let's actually do X. Okay, this X has no binding. Okay, so let's actually delete this one. We have a broken area. Okay. So let me actually delete this one as well. Okay, delete this one as well. So let's save. Okay, so let's actually run it one more time. Okay, there's a 3, and then I eval my X. Okay, and I do eval 3, eval X. Okay, you get 3. So in right here, you do evaluations. Okay, because you had a binding, and right here, you do not carry the binding to this eval X, so it's not allowed. Okay, so that's what it happens. So remember that here you do not build the reference environment, but here you do have. Okay, here you do have. So that's one more thing you need to know about. But how can we actually make the top quotient to work? Okay, how can we check make the top quotient to work? So that one doesn't work. So we need to define some namespace for the eval function to work. Okay. So here we do this. Okay, so let's actually define NS as make base namespace. Okay, And then everything after that, we can actually set the binding to our namespace. So let's do this one, okay? So let's do this one. Let's actually try this one, okay? So let's define ns as make, okay, base, okay, namespace. Okay, this is somewhat like when you do C++ programming, you say using namespace, okay, std, okay, similar to that. So we create this, and then we will do this, okay. We will do here. Here define, okay. No, let's do this one. That we will actually do evaluate, okay, evaluate. We will make the definition available for my namespace, okay. So that will put into my namespace. So evaluate define, okay, xf10, okay, and this one put into ns, okay, put it in. So right here, if I eval x, okay, actually, and using ns, okay, let me see. Okay, we using eval something using ns, okay. NS is the namespace. So let's try this one. And let's save and let's run. Okay. So second one that actually we no index. So that this one, let me actually take it out. Okay, let's take this one out. Okay, let's run it. Okay, so you get 3, 3. So this one actually worked. Okay. By bypassing that one, you will evaluate x based on your namespace. So this is the way you use the namespace to build your environment. So right here, if you put it over here, you simply do eval x, okay, you get 3. Then you do eval x, and then using ns, you will also get 3, okay. Okay, that's actually is the namespace, okay, namespace is to, when you use the eval function, you may use it, okay. If you don't use eval function, you are okay, your reference environment should be fine, okay. Okay, so there's an apply function. You can apply function to certain data. Okay, you can apply plus to it. So this apply may be similar to the reduce function. Okay, maybe similar to the reduce function in the Python. Okay, apply is similar to reduce in the Python. So let's do this one. We actually may do this. We may do apply. Okay, let's apply. Multiply to 1, 2, 3, okay, something like that. Okay, so let's save and let's run, and we get a 6 for the multiply result of it. Okay, okay, that's actually similar to the reduce function in Python language. Okay, so that's the apply function. And then scheme feature, okay, you have lexical scoping, dynamic scoping, typing, function as first citizen, tail recursion optimized. Okay, these are some features. So we encourage tail recursion, and we have these different rules. Okay, so first class citizen in the programming language is that you can pass it as parameter, return it as a result from subroutine, and also assign the first class object to available. Here we emphasize on the functions. Okay, so you can map function and using function as a parameter to the list. Okay, and you can map number check-in to all these. Okay, you can map this lambda to all these. This is the so-called map function. Okay, higher order function. So map, filter, and apply. Apply not actually being support. So you use apply. Okay, reduce not supported. So you use apply for this one. Okay, so that's the functional programming. Okay, here it show you the map function. Okay, mapping the number checker to this and this. Okay, the whole thing. Filter, you actually take out the element that qualify for numbers. Okay, so something like that. It's the filter function. And the last one, reduce. Okay, reduce, you have to define your own reduce function, but you can also use the so-called apply for it. Okay, so you apply this to here. Okay, that would be okay. So that actually is initial value. Okay, this is one initial value. So you can apply for it. Okay, you get apply plus. So let's try this one. Okay, try this one. We don't use the so-called, here we already show you this. We don't use reduce, we use plus. Okay, 10, 20, and 30. Okay, and then let's save. And that's actually wrong. Okay, so it actually get this result. So apply similar to reduce in Python. Okay, apply similar to reduce in Python. Okay, so this portion, when we study this the so-called scheme cheat sheet, we look into different examples. Okay, we look into different examples. So right here, we actually finish this one. Finish this one. Let's actually go on this one. Implementation issue. There are several different implementation for scheme interpreter. Okay, and there are also compilers. Okay, conceptually, at least everything is a pointer in a scheme language. Okay, you can also call it reference, and everything is located in a heap. Okay, garbage collection. And reality, small runtime written in C, C++. So scheme compiler is very tiny. Okay, it's very tiny. So it's very good in terms of area saving. Okay. If you want to just use a scheme as an interpreter and do computation. Okay, so we define function x. Okay, and then if end test. Okay, end value. Okay, and augmenting function, and here. Okay, this one is recursion. Okay, so here you have the base condition and also augmenting function. So here we define n factorial. So here if. So if is actually what base condition, okay, and so if you would have if, and then expression, and then true portion, okay, then portion, and then else portion expression, okay, two expression here. So this one is that used for base condition. This one is used for recursive condition, okay. So the basic function for recursion. Okay, tail recursion is that you apply the function and you won't need any more operation on the function call. Okay, we call it tail recursion. So here, all positive, you actually do null list, you return true. Okay, and then here actually if you call number is less than equal 0, you will return false. Okay. And your data should be, you will return the else portion. Okay, so all part you will apply your alternative. Okay, and then you actually on the rest of the list. Okay, so the list is actually empty, you return true. Okay, and if any one of the element that actually is false, then we will return false. Okay, so that's that. Okay. Special form, we have defined lambda quote not if condition and or and evaluate. Okay, these are special forms, special functions for the scheme language. Arguments are passed to special form without evaluating them. Okay, special form have their own rule for evaluation of arguments. Okay, this is known as normal order. Okay. So scheme example, we construct a program that actually simulate a DFA. Okay, this DFA is from Scott's textbook, third edition, page 521. Okay, this textbook we already give the link for you. So what you can do is go to your account. Okay, right here. Let me close it. Okay. Here, let's actually go to the Louis account. Let me pick the course. Okay, let me pick the course breakball. Okay. Let me pick the programming language course. So here I pick the Spring 2022-003, this one. And I'm going to look at the start here, okay? So start here, I have syllabus. Okay, let me go back to syllabus, okay? Go to syllabus, and on the syllabus, we do have reference book. So look at the textbook, third edition programming language programmatics, okay? So right here, you can download this book, okay? You can download this book. So you can download this book, and that's a certain that you download. So I'm going to use my local copy, okay? So I'm going to use my local copy. So you go there and you can download that one, and you should be able to find the textbook on page 521, okay? Page 521. So here, let me pick the school, look at the textbook, okay? Now here, let me go back. So I'm going to here, going to the textbook here, programming language programmatic version 3, okay? Page 521. 521 is chapter 10, the so-called, okay, here we have chapter 2, let me see. It is chapter 10, functional programming, okay. So this one is 505, so let's say you continue. So 521, okay, let's actually go down, okay, go down. Okay, so page 521, we are looking at this finite state machine, okay, this finite state machine. So this finite state machine have been coded into this example, okay. Let me show you one more time. It's actually in this programming language programmatic book, chapter 10.4, evaluate order revisit, page 521. Okay, we are talking about this finite state machine. So the same finite state machine being written into scheme language. Okay, into scheme language. So let's look at it. Okay, so here is the finite state machine, and then we write it down in scheme language. Okay, so I don't go into the detail for this given step, and then we do simulation, okay, based on some input. So this one is a finite state machine, and you provide this input sequence, and you get some result. Okay, you get some result. So that's the simulation of that, and we do get give these, you go through these different steps. So Q0, Q2, Q3, Q1, okay. You go through this finite state machine, and eventually you go through everyone and you do a set, okay, because you reach certain final state, And the other input, this one, it goes through the different state, but actually it is rejected, okay, it is rejected. So here, what we look at it is actually, the program itself is a definition of finite state machine. Okay, this one is the simulation and the definition of finite state machine. And when you run it, you need to put a finite state machine to there and input sequence. Okay, so this one actually, the DFA is the finite state machine. DF determinist finite state machine automata. And your input in provided over here. So the whole program is very small, okay? The program is small, and you provide some output, whether it's accepted or rejected, okay? If finally it reached the final state or not, okay? And there's a move function to make transition between different states. So right here, this portion is your finite state machine description, okay? And your input is over here, okay? And then you get this different result. So summary, okay? Java and Python are very powerful real-world language, but they often struggle as language for learning, okay? The extra syntax they have for enabling programmers to easily access the more advanced feature quickly complicated the whole matter. That's defeating the point or being easy to use. Okay, but this language, okay, these two language, okay, they are defined, they are used for the desktop language, okay, and Scheme language is a simple language. It just used in the interpreter format, and it supports functional programming. So it is a simple and ideal minimalistic language, and good for interpreter design and quick turnaround for programming. Okay, so this is the conclusion of chapter 7, lecture 9. Okay, thank you, and let me know if you have any question. Bye now.